Assalamu alaikum, bismillah ar-Rahman ar-Rahim. Today we are going to answer Unit 3, May-June 2021, okay, for edexcel, okay. As you know that Unit 3 has 4-5 questions about practical physics, okay. They ask to investigate certain experiments, okay, according to Unit 1 and Unit 2. So for example, here in this question, they ask about density. What they ask? A student planned an experiment to determine the density of actinium. Okay, what they said? She was given, okay, a pack of 50 sheets of it, okay, and has the access to what standard laboratory apparatus. The approximate dimensions of a single sheet is given: the length, the width, and the thickness of what a single sheet. Okay, the total mass of it is approximately 670 grams. Okay, they give us the units here in centimeter, and here it's in millimeter. We have to convert it into what? Into centimeter, and we have here the mass in what? In grams, or we can convert everything to become kilogram per cubic meter. Okay, part A, what do we have? To determine the density of it, the student needs to take measurements. Complete the table below. They give us mass, length, width, and thickness. The mass, we use a balance scale, okay. The length and width, we are going to use the meter rule, and the thickness, we are going to use the vernier caliper or the micrometer. Okay, he's used what the vernier caliper. Now the resolution of the length and the width, since they give us dimensions in centimeter, I'll put the resolution as what? Centimeter. What's the resolution of the meter rule in the centimeter? It's 1 milli, so it will be 0.1, yes, centimeter. Thank you, Kareem. Thank you, Ahmad. Okay. Also the thickness, okay, here they give it to us in millimeters, so I'm going to give them the resolution in millimeter, and for the vernier caliper, it's what? 0.1 what? Millimeter. Okay, yes, thank you, Ahmad, and thank you. Okay, good. This is one easy mark. Next, part B, what they ask. Discuss a method to determine the accurate value of the density of it. Okay, now we need to find the accurate value of the density. Now what do we have to do here? If I want to find the accurate value of the density, okay, we need to take all the measurements as accurate as possible. So, and we have to find what? The average, the mean. So we'll measure what? The length and the width of the 50 sheets by a meter rule at several positions and find the average. Okay, or the mean. This is the first mark. Second mark, what do we have here? I think then what? And then measure the total mass, measure the total mass of the 50 sheets, then what? We're going to say that calculate the density. We are going to write down the formula. Density equal what? Equal mass over volume. And we have to be more accurate about what's the volume here. So which is mass divided by what? length times width times height, or times thickness. Good. I think that here we get the 5 marks. Take screenshot. In part C, what do we have here? The student then follow the same method using a thicker sheets of it, of actinium, Explain why using thicker sheets of it, will reduce the uncertainty of her value of density. Now, we know that whenever the things that we need to measure, it's bigger, that means that the percentage uncertainty it will reduce, since we are taking the values with the same precision, or with the same resolution. So what we're going to say here, since the uncertainty I'm sorry, of the measurements will be the same and the value of the thickness is greater so the percentage uncertainty of it will reduce. Okay, good. So we are trying to find the percentage uncertainty as small as we get by taking bigger values. So that's why I choose 50 sheets. Okay, it's better than to measure one sheet. Okay, so whenever to measure the length and the width. So whenever the number of sheets is bigger, okay, or the dimensions that I would be more, that means I will be more accurate, since the percentage uncertainty it will be lower. Okay, this is question number 1. Let's move on to question number 2. Question number 2 talks about standing wave. It's obvious from the figure. What they say: a student determined the speed of sound in air using a standing wave. The student used the tuning fork, to create a sound of wave in a column of air inside the plastic tube. We have a plastic tube and we can control how much deep inside, so how much is the length, from the water surface to the top of the tube, that start to make booming standing wave, creating a louder sound. He placed the plastic tube, into the measuring cylinder and, to the water, So he could adjust the length L of the air of column. As you can see, it's not to scale. The student adjusts L until what a loud sound, is heard, indicate that the standing wave has formed, He marked the water level, on the plastic of the tube and measured by length L, as you can see here from the top to the water level when there's a loud sound is heard. Now, I told you several times they give you 3, 4, 5 lines, about doing the experiment, and now they assume that you are expert, about this experiment. Now, this experiment, we already know it, because, usually most of the experiment that they bring in Unit 3, we already know it because we study it in Unit 2 or Unit 1, but sometimes it's not, So he repeats this process several times, and the results was like this. So he repeated 1, 2, 3, 4, 5 times. So just two reasons for the variation of the length of the student measurements. Why it's hard to measure this length, and that's why they are not that close to each other. You can see there is a range of difference in the values here. Why it's difficult? Because it's difficult to know exactly where's the loud sound because of the noise surrounding you in the lab, especially with the students, That's one of the mistakes or one of the problems of doing this experiment. And also when you mark, okay, on the water level, it's still, you need to what to move with, you need to move the tube so it will not be as accurate as possible. It will, if you will not stay at its position, okay, especially with your hand or with one of the students' hand. So it is difficult. It is difficult to find at which distance the sound will be, the sound will be the loudest due to the noise, okay, from the background, yes, I will not mention students now, okay, okay, and also cannot hold the tube without movement, okay, without movement. To mark the water level. And maybe it's not vertical. And maybe it's not vertical. Okay, so these are what the ideas of how we, in reality, when we do this experiment in the school, okay, why we cannot have an accurate value. Next part here, what do we have? Part BI. Calculate the mean value of L. Now let's look here to the values. We need to find the mean, and the mean will be the average. So that means, okay, L dash, okay, equal 18.4 plus 18 plus 12.2 plus 19.4 plus 19.2 divided by 5. And by using calculator, how much is the answer? It will be 18.8 watt centimeter. This is the what? This is the average. Okay, good. Mister, when should I decide it's normal or not? Because in chemistry, it's within 0.2. Okay, look here. How we can decide that if there is a value, anomalous value or not? If we look to the values here, okay, you can see that I can't decide that this one is anomalous value since it's not that far. And actually, the average, which is 18.8 that we find it's not of neither one of these values. And you can see that both of these values are small and these three values are big. So that's why we take the average. But it's obvious if we have what? If there is an anomalous value which is very far, okay, we can see that it's not what? It's not in the range of the accepted answer. So sometimes, yes, we need to neglect it because it's too far or too big or too small from what the main values, okay? Now here it's written, it's in centimeters, so that's why I put it in centimeter, and it cannot be 18.4 meter. It's not a building, it's a measuring tube, so it's supposed to be in few centimeters, okay? Now maybe you can convert it or not. They didn't ask to convert it. If you want to write it down as, okay, as converted, you can do that, doesn't matter. Okay. Next, calculate the percentage uncertainty of L. Now, since we have several values, okay, We are talking the range of minimum and maximum, okay, and divided by 2. And this will be what the uncertainty of this of the mean of the value of L. Again, first of all, we need to find what is the uncertainty. So the uncertainty is equal maximum value minus minimum value in this situation, divide by what? Divide by 2, which is the range. They call it the range, okay? So the maximum value, which is 19.4, minus the minimum value, which is 18, okay? Divide by 2, and by using calculator, it will be how much? How much it will be? It will be what? 1.4 centimeter. Now, this is what half of the range, okay? Now I need to find the percentage uncertainty. The percentage uncertainty, it's equal the uncertainty divided by what? The value multiplied by 100 what? Percent. So the value that we have at 1.4 divided by the value that we got it 18.8, okay? Multiply by what? Okay. It's 0. Okay. Thank you. So okay, it will be 0.7 here, I'm sorry. Okay, 0.7. Okay, so 0.7 divided by 18.8, multiply by what? Multiply by 100%, and the value, it will be how much? It will be 3.7%. So the percentage uncertainty, it will be 3.7 what? Percent. Yes, thank you. I fix it. Yes, thank you. Good. Okay, next. What do we have here? C. They said that here, the frequency of the tuning fork was 440 Hertz. Most of the schools lab, they have this tuning fork with the frequency of 440 Hertz. The standing wave is produced that has a wavelength of what? 4L. Now, this information, we have to know it if we are studying Unit 2. Look here. This is the said about the first what? Harmonic, that it will be somewhere here like this. Okay, do you remember this? Okay, we talk about that in the course. This will be the first harmonic. This is a quarter what wavelength, because the complete a continuous wavelength to complete wavelength would be something like this. So it actually what? Only what? Quarter. That's why they give us what? They give us this information that the wavelength is 4 times the length. Okay. Now calculate the speed of sound in air. Now we know that the wavelength is equal 4 multiplied by L, the distance L that we just find it out. So 4 multiplied by 0.188. Okay, I convert from centimeter to meter, which is 0.752 meter. Okay, this is the first step. Second step, okay, we need to know how much is the speed. So speed equal frequency times wavelength. So it's 440 multiplied by the wavelength, which is 0.752. And the speed of sound in air, it's approximately 331 meters per second. Good. Okay, take screenshots for the answers here. Okay, next. See, the percentage uncertainty, okay? The percentage uncertainty and the student's value of the speed of sound is equal to the percentage uncertainty of what? Of L only, okay? The accepted value of the speed of sound in air is 343 at this temperature, at this situation, okay? Comment whether the student value is considered to be accepted value, okay, of the speed of sound in air or not. Now we know that the speed of sound in air, it's how much? 331, okay? So I would say that it will be plus minus, okay, the 4%. So 331 plus minus what? The 4%. That means what? That means the maximum value of the speed maximum, okay, and speed what? Minimum, okay? It will be from what to what? This is the value of the speed, okay? It will be 331 times 104%, okay? Or 331 times 0.96%, and the value is here. How much is the value? 343. Okay, to how much? Who has a calculator to multiply these two values? How much we get? 331 times 0.96, 318. Yes. So is this value 343 within the range of the student value? Yes, it is with. So 343 meters per second is within the range. So it is accepted value. Okay. How do you okay, what do we mean by 4%? This is math. When we said that 4%, what do we mean by 4%? That means it's 100% plus 4%, okay, or 100% minus what? 4%. So you can find how much is this 331 times the 4%, then you add it to the value 331 or subtract it. So I did the same thing here. This is math, okay? You know how to do it in math. Okay, you are welcome. Next, question number 3, what do we have? A student determined the viscosity of a liquid. Okay, the student measured the force required to pull the small sphere upwards through a liquid at constant what speed to be balanced. So the resultant force is equal to what? To 0. So he can find out the values, okay, as we study in unit 1. Okay. A student measured the diameter, okay, of the sphere using what? A micrometer. Now we know that how to use the micrometer. Okay, we have 5, 10, 15 until here. Okay, so we have 17.5 plus what? Plus the value that's exactly in front of it, which is 0.40. Okay, so that means the diameter here, it's equal to how much? 17.9 what, or 90 what millimeter. Again, let me show you what we did here. Okay, I would zoom in. Okay, and what do we have? How we can take the reading of the micrometer? So we have 5 millimeter, 10 millimeter, 15 millimeter, then 16, 17, 17 and a half millimeter, and extra. How much is this extra? Is this the line? Okay, okay. So how much is this? This is 40. 40 divided by 100. Okay, because every one complete revolution, okay, it's half millimeter, half millimeter, half millimeter, half millimeter. So 2 complete revolution, it's 1 complete millimeter. So that's why we divide by 100. Okay, good. So this is what? This is the diameter. Okay, 17.90 millimeter at the dimensions they give it to us. Now what they ask here, okay, calculate the percentage uncertainty of the diameter, okay, of the sphere, okay, shown here. Now you know that, okay, you know that if I want to find the percentage uncertainty, okay, the percentage uncertainty is equal to the uncertainty divided by the value multiplied by 100%. Okay, we talk about that several times. What's the uncertainty of the micrometer? What's the smallest reading of the micrometer? It's 0.01 millimeter. So this is the smallest resolution. I will divide by what? Divide by 2. I told you it's plus minus half this value. Okay, plus minus half this value. Okay, why? Because I don't have like a meter rule, 0 error on both sides, okay, or half resolution both sides. So I will not write plus minus, okay, 0.01. I will say it's because I have only one reading from one side. So plus minus 0.01 divided by what? 2. Okay, this is the resolution. So it will be 0.005. Okay, this is what the uncertainty. Okay, divided by the diameter, which is 17.9, multiplied by 100%, and by using calculator, it will be how much? 0.028 what percent? 0.28%. Good. Is it clear? Okay, let's move on to next part. State one precaution that could be taken before using a micrometer. Now, any instrument, we need to to use it. It has problems, okay? So if it's digital or analog, if for example here we have analog, that means I have to check the zero error, okay? I have to avoid parallax error, okay? I have what to every instrument has a problem. Here, because I have micrometer, I have what to check the zero error. If it's digital, I have to check that if it's correct or not, if it's on the scale that we have to use it or not, okay? Like the multimeter. We talked about that the last time, and we are going to repeat it before the exam, inshallah. So check what the zero error. Check the zero error before using it. Good? Clear? Okay. Next part. C. The student measured the value of the force when the sphere was suspended and what stationary in the liquid. The force meter used in the photograph was shown. Okay, what is the reading here? 1, 2, 2.5, 2.6, 0.7, 0.8, 2.9. Okay, and the unit is what? In Newton. Okay, continue. When the sphere was stationary, the reading of the force meter was what? The reading of the force meter was 0.020 Newton. When the student moved, okay, with the force meter upwards, the sphere what? Okay, move with a constant speed of 0.32 meters per second. The reading was 0.92. Okay, I'm sorry, 0.92. I just noticed that there is 0 point here. Okay, so 0.29. 0.29. Okay, good. Let's see what they ask. First part, what do they ask here? Okay, explain why it was necessary to measure the force when the sphere was stationary and the force when the sphere was moving at constant speed. Now let's go back to the picture here. Now when it is stationary, what is the forces act on the sphere? Who can tell me? This is the sphere and it is stationary. What are the forces act on it? Yes, there is weight downwards, okay. And what else upward? Exactly, there is what? There is the force of tension plus what? Plus what? The upthrust, okay. Type. Maybe we neglect the upthrust. It is small dimension, okay. And when it was moving upward at steady speed, okay, constant speed, there is weight, okay, downwards, and there is what? Tension plus upthrust upwards. And now, because since it is moving, okay, there will be another force downwards, which is what? The drag force, right? Okay, here it was stationary, there is no drag force. And since we need to find the viscosity, I need to know how much is the drag force. So that's why I measure the force before and after, because when it was stationary, there's no drag force. When it's on motion, I know how much is the drag force. So that's why I did this. When it was stationary, okay, the reading, okay, T is equal to the weight, what? To the weight W. Okay, minus or subtract the upthrust. U. Again, tension is equal, okay, sorry, tension plus tension plus upthrust is equal to what? To the weight. But as it moves, it is moved upward, the tension is equal T equal W. Okay, let me write it here in a new line. T equal W minus U minus what? D, right? Where D is the drag force. D is the drag force that we need to what? To find it out. Which is needed to find it out. So subtracting the readings, give us the drag force. Okay, good, clear. Is it understood why we do this? Yes, thank you, Ahmad. Yes, weight and upthrust. Mr. Y, it is minus D. Okay, now again, if you look here to the picture again, we said that it's moving what? Upwards. I'm sorry, plus D. I'm sorry. Yes, my mistake. Okay, plus D. And subtract the readings, give a positive value of D. So, yes, you're correct, Ahmed. Then what they ask here, calculate the viscosity eta of the liquid. Now we know that drag is equal to the difference of tension, which is 2.9 minus 0. Minus 2, okay, which is equal to 0.9 in Newton. And we also know that drag force equals 6 pi r eta v. Okay, we need to find eta. So eta equal the drag force divided by what? 6 pi r v, which is equal the drag force 0.9 divided by what? Divided by 6 pi. What is the radius? Who can tell me what's the radius? What's the radius? Exactly, it's half the diameter. Bravo. It's half the diameter. And the velocity, how fast was the velocity? How fast was the velocity? Where is it? The velocity is 0.32. So the diameter, 17.9 millimeter times 10 to the power of -3 meter divided by 2, okay, to be a meter, all multiplied by what? By the velocity, which is 0.32. And by using calculator, the answer, it will be 1.67, okay, or 1.7 Pascal dot second. Good. Is it clear? Take screenshot here. Yes, Ahmed, تفضل. What's your question? Drag only exists when it's moving. Yes, we say that when the speed increases, air resistance increases. When there is motion, there is drag. But when there is no motion, there is no drag. Okay? Good. The motion, okay, causes what? The drag. It increased by the drag. So whenever there is no motion, there is no resistive force. The drag is the resistive force of the motion, okay? The fluid or the water or the air, okay, will be okay, in the opposite direction on the object as it moves, okay? The opposite direction of its motion. Part D, what do they ask here? They say that the resolution of the force meter is 0.01 Newton. The distance moved between the rubber bands was 25 centimeter. The time measurement is what? The time measured was 0.78 seconds, okay? The percentage uncertainty of measuring the diameter is negligible. It's very small. I remember it was 0.027 or 37%, which is negligible, yes. Assessed whether, okay, which of these measurements was the most significant source of uncertainty in this, okay, the value of the viscosity. Now look here. Now the force meter, we can find how much is the reading, okay, the percentage uncertainty for it, okay, which is 0.9 or sorry, 2.9 or 2.0, okay, and we will divide how much the percentage uncertainty of the reading with the values that we read it, okay. The distance, it's usually in centimeter, and the smallest precision for the meter rule is 0.1. We will find it out. But the problem here is what? Is the time. Look how long is the time. The time measured here is 0.78. So he pulled it with a constant velocity upward, 25 centimeter and 0.78 seconds. So the distance has a small precision, okay, or the smallest reading or the resolution 0.1 centimeter. The force meter 0.01 Newton. But the time, I'm not talking about the stopwatch here. The resolution may be 0.1 or 0.01 second. I'm talking about what? Exactly. Huh? I'm talking about what? The reaction time. The reaction time can be approximately 0.3, 0.4, 0.5 seconds, depends on the student. Okay, so the reaction time 0.2 or 0.3 or 0.5 seconds, it's a huge value compared to what? To this measured time. So which of these values is the most significant on the uncertainty of the viscosity? Is measuring the time. So what I'm going to say, I'm going to find how much is the percentage uncertainty for each of these values: the force, the distance, and the time. So the percentage uncertainty of each can be calculated as shown. Okay, let's start with what? With the force. So force, we will say that 0.01 divide, for example, by 0.29 times 100%. Tell me how much is the answer, if you please. This is the first one. The second one is the length, and it's 0.1 divided by 25 multiplied by 100%. Give me the answer. The answer for the first one was how much? Yes, it was how much? Okay, good. 3.45, okay, percent. The second one, how much it is? 0.4%, okay, 0.4%, okay. The last one, which is what? The time. Let's say 0. How much is the reaction time? 3 divided by what? Divide by the time, which is 0.78 times 100%. The reaction time usually between 0.2 to to 0.7 seconds, okay? It doesn't matter. I want to show them that it will have a high value. Let's say 0.2, 0.3, 0.4. I want to show them that it will have a high value because this time is too short. Okay, Ahmed? Okay, so how much is the answer here by using calculator? How much is the percent here? Okay, it's a huge value, 38%, 88.5%. So let's say here, now let's go to write down the time has highest effect, okay, since the reaction time whenever that reaction time is bigger, okay, from 0.2 to 0.7. Yes, maybe some of you get 1 second reaction time. That's why a lot of people get accidents, okay. I'm not going to say especially females because their reaction time is slow. Some females, they have high reaction time, okay. So it depends on the person himself, okay. So the time has highest effect since the reaction time is what? Long compared to 0.78 second time measured. Okay, good. Now a lot of comments will come down here on the YouTube when I talk about male and female reaction time. Any question here? Is it clear now? Okay, let's move on to question number 4. Question number 4, what do we have here? The activation potential difference PD of is the minimum potential difference for photons to be emitted from the light emitter diode, okay, LED. The student measured the activation potential difference for different LEDs, okay. The relationship between the activation potential difference and the wavelength is given by this equation: EVA, okay, equal Planck constant C over speed of light plus W, where VA is the activation potential difference, okay, and lambda is the wavelength of the photo emitted. W is what is the constant to represent the work function, okay, by an electron passing through the LED, and E is the charge for each electron, okay. A, explain why the graph of VA against 1 over lambda should be what? Straight line. Should be straight line. Now let's rearrange this equation between VA and these values. So I will divide over E, okay, VA equal HC over E lambda plus what? W over E. That means VA, it will be equal HC over E multiplied by 1 over lambda plus W over E. And this equation is similar to what? To this equation, Y equal MX plus what? C, since they say that this is supposed to be in the y-axis and this is supposed to be in what? In the x-axis, VA against 1 over L. So yes, the gradient equal HC over E, and since all these values are what? Are constant, and since all these values, okay, are constant, okay. Good. So yes, it is a straight line. It is, so yes, it is linear shape. It's a linear relationship. Yes, it is linear relationship. Okay. Next. B. The student record the values of the activation PD, okay, and the manufacturer corresponding values with the wavelength, okay, lambda 10 to the power of negative 7 meter, and the activation in voltage, and these are the values, okay. We have column here, which is not included. Complete the table with the corresponding values of 1 over lambda. So that means 1 over what? 1 over meter, right? Or per meter square, the unit. Okay. So we can put it in what? In 2 or 3 significant figures, and you can see that it will be times 10 to the power of what? Positive 7 or 6 per meter. Okay. Give me the values if you please. 1 over 6.6, how much it is? Yes, thank you, 1.52. The next one, 1.63. The third one, 1.71. Then 1.89. I'm sorry, I skipped one. Okay. 1.69, 1.71, 1.89, and 2.13. Okay, these are the values. You can see I wrote it by the same values of significant, 3 significant figures, right? And the value it will be to the power of 6, and the unit is per meter. Then what they ask here, after we finish these values, okay, plot the graph between activation voltage in volt, okay, on the y-axis, and 1 over lambda in what? In the x-axis. So I'll write here 1 over lambda slash times 10 to the power of 6 per meter. Okay. Now, since I'm talking about a straight line, and I'm talking about linear relationship, that's supposed to be what? Starting from 0? Well, it's not necessary to start from 0, right? No, it's not necessarily. So, okay, what is the smallest value that I have here in the voltage? It's 1.8. What's the greatest value? It's 2.58. So that means I will make my curve starting from, let's say, let us check how much is the value. Okay, if it's 1.8, that means I'll start from 1.7, 1.6, something like this. Okay, so if it's I start from 1.6, and the maximum value it will be how much? It will be 2.58. So let's say that's here 1.6, 1.8, 2.0, 2.2, 2.4. Yes, it's enough. 2.6. Okay, it's good curve. Okay, y to the power of 6. Use your calculator. Use your calculator. If I divide this value, okay, 6.6, okay, times 10 to the power of negative 7. If I put 1 over it, how much is the answer? The answer it will be 1.52 times 10 to the power of 6. Right, Ahmed? Okay. Now let's move on. So after we put these values, I'm going to do the same thing for 1 over lambda, and the smallest value for 1 over lambda was 1.5, and the biggest value was 2.13. So let's start from 1.4. Okay, and here it's 1.6. Here it's 1.8. Okay, and here 2, and here 2.2. Did I cover all the values? Yes, I cover all the values. So this is a good curve. Then I'll put what the points. The first point, let me look again here. Okay, it's 1.8 with these. Okay, so I put the points. Okay, 1.82. Okay, with what? 1.82 with 1.52 somewhere here. Okay, and I continue plotting the graph. Let me check how they plot it on the mark scheme. Okay, they give us here. Yes, look here. They try to draw the best fit curve, okay, best fit line, straight line, okay. And as you can see, they will ask us to find the gradient, and you will see that the gradient here, they took a point which is intersection, okay, clear intersection with a clear point, which is, we know the coordination of it. So they draw the triangle, okay, that means we're going to draw the triangle now to find the gradient, okay, and we have to know what is the rise and what the run. So we have to choose these points carefully. Okay, Ustad, I didn't use these points. Can I use this one with this one? Yes, of course, but whenever the points are further, you will be more clearer, okay? Can I choose a point somewhere here at the end? Yes, no problem, okay? So whenever the points are further, and you can see that they didn't plot the points, okay, according to the first one and the last one, okay? It didn't pass the last one. Maybe it passed the first one. So that's why there's curve of the accepted answer. It depends on your drawing and how accurate you are, okay? So let's go back to the question. After we do this, what do they ask? Determine the value of the Planck constant, okay, from the data sheet. Now we said that the gradient equal what, ya shabab? What did we say? That the gradient equal what? Let's go back to the linear relationship that we find it out here. That's the gradient is a Planck constant multiplied by speed of light divided by E, the charge for each what electron. So we'll say that the gradient here equal hc over E. Now I want from you, if you draw it, to give me how much is the gradient, how much is delta V over how much is delta 1 over lambda. Give me the values, if you please. Draw it, and yes, if you draw it before. Okay, I think that the mark scheme suggests a value. Okay, is this your gradient? Okay, thank you, Karim. 1.3 times 10 to the power of -6. That's his gradient, Karim. It's equal to what? To Planck constant that we want to find it out, multiplied by speed of light, which is 3 times 10 to the power of 8, divided by what? Divided by E, which is 1.6 times 10 to the power of negative what? -19. Let's do cross multiplication and find out how much is the value of H. Use the calculator, multiply this by 1.6 times 10 to the power of -19 and divide by the speed of light. How much is your value of Planck constant? How much? Multiply, yes. Multiply this by this, divide by 3 times 10 to the power of 8. Okay, now your value, okay, it's out of the accepted answer, so you lose a mark out of 3. Okay, it's 6 point what? 93 times 10 to the power of what? 6.93 times 10 to the power of what? -30 what? 4 joules. Now, it doesn't matter. You don't know the mark scheme. Neither I don't know the mark scheme during the exam. So this is my answer. I keep it. Okay. I keep it. Okay, I can see that the value is too far from the real value, which is 6.63 times 10 to the power of -34. But okay, maybe your drawing is a little bit has a greater gradient, okay, steeper than what the accepted value. Okay. Could this be due to the incorrect plotting of the graph or what? No, it depends on not on you. I don't think that you will plot incorrectly. I think that you make your line steeper a little bit. Yes, Ahmad, what's your question? How do we work out the equation? Let's return back to the equation. They give it to us. Look here, they give us the equation. I didn't do anything except I divide over E over E. So this E with this E cancel out each other. That's what happened. So VA equal Planck constant C divided by E lambda. So I put lambda separated. So 1 over lambda HC multiplied by E since lambda is in the bottom. And that's it. Good. Which equation? This one? The gradient. Okay, the gradient from the equation, I found this gradient. Now, as I told you, we can plot how we can make it a sub-pitch. Okay, the gradient, whatever this is the value of the gradient. Let me change the color. Okay, this was what the value of the gradient, right? All this is equal to hc over E. So I'll do cross multiplication and find C by its value. So it will be hc equal this value, the gradient, okay, multiply by E. Yes, okay, good, good. No problem, Ahmed. Okay. Now your value is a little bit far from the accepted answer, but you don't know, okay, Kareem? So let's skip it, okay? Now, what they asked then? The students state that the value of the Planck constant obtained by the graph is inaccurate. It's obvious, it's inaccurate. Evaluate the student statement. What do you think? Huh? Is it inaccurate? How we can check that? It is inaccurate. Look what we will do. We will say that the percentage uncertainty for your answer is equal to the difference of the values divided by the value multiplied by 100%. What do I mean? Look here. 6.93 minus 6.63, okay, right? Divided by 6.63 multiplied by 100%. Okay? Now tell me how much is the percentage here for your for this answer? How much is the percentage uncertainty? 6.9, okay, it's 4%. So you can say it's what? It is 4% above what? The real value, which is 6.63 times 10 to the power of negative 34 joule per second. Joule dot second, sorry, joule dot second. Okay? Which is very small, which is small. So yeah, so it is accurate. So it is accurate. Any value less than 5%, any value less than 5%, we assume it's a small percentage uncertainty. Okay? Good? Okay. Take screenshot. Next. Each LED, okay, in the investigation emits through a narrow wavelength, okay, a narrow range of wavelengths, narrow range of wavelengths. The wavelength values stated by the manufacturer of the wavelength of light it's emitted with maximum intensity when the LEDs at normal brightness, maximum light intensity at normal brightness. The wavelength is emitted at activated potential difference is not equal to the manufacturer value. Discuss whether this affects the accuracy of the value of the Planck constant obtained. Is this the reason or it's not the reason? Now, when they say that the manufacturer maximum light intensity with normal brightness has narrow range of wavelengths, okay, what that means? Yes, thank you. That means, okay, whenever the wavelength is shorter, for example, okay, that means the frequency of the photon, it will be less, so it needs less energy, okay? So yes, shorter, that means, sorry, higher frequency, so higher energy, right? Okay, so at lower wavelength, okay, that means give a higher value of 1 over lambda because we are plotting a graph between 1 over lambda, right? So the whole line may be shifted to where? To the right, okay? And maybe, okay, for smaller values of 1 lambda, the 1 over lambda, it will be more what? More shifted to the right, that means the gradient will be less. So this decreases the value of what? of Planck constant. Again, I'm talking about what? Planck gradient here, right? And the gradient is equal to what? Planck constant multiplied by C over what? E. And the formula V equal what? HC over E, 1 over what? Lambda plus W, okay, over E. So whenever the gradient is different here, okay, how the gradient is changes. Now actually I change this value, the wavelength. So whenever the wavelength is shorter, for example, that means the frequency is what? Higher. That means the energy, it will be what? More, because they said at normal brightness they do that. It's okay. So that means the value, okay, all the values, they will be shifted to what? To the right. And maybe the small values, okay, they will be shifted more to the right. That means the line will what? Will get what? Yes, less, the steepness of the gradient will be what? Will be less. So that affect the value of what? Of h. Since this v, it will remains constant, right? So let's look to the mark scheme, what they said here. In the mark scheme, yes, this is the last part here. The manufacturer, okay, value, okay, would be shorter than the wavelength of the photons, okay, that would have least what? Energy. Or the manufacturer wavelength will be what? Shorter than the wavelength obtained by the frequency emitted by what? By the activated voltage. So that means a lower voltage will give what? A higher value of 1 over lambda. So when I say that the higher value of that 1 over lambda, that means all the points, okay, of the longer wavelength will be shifted with what? 1 over lambda less value. That means the gradient will be what? Less, decreasing the gradient. So as the gradient is decreases, okay, that means the value of the Planck constant, it will be what? It will be less. Okay, that's what I said. The other answer, okay, they said that what? Different values of wavelength will be smaller, so it will be negligible on the what? On the shift of this point. All the graph will be shifted. Okay, so there's no change of the value of h obtained. I don't think that the student will do that. If in reality, if we do this in reality, we will get what? The second answer. Okay, now in the beginning here, the manufacturer wavelength, okay, will be what? Shorter, since the photons has least frequency, okay, least energy to what? To get out. Because why least energy? Okay, let me ask you, tell you what least energy. Well, they said in the beginning here that, where is it? Here they said that the student measured the activation for different minimum potential difference, minimum energy needed, okay, to release what? The electrons. So that means least frequency, greatest wavelength. Do you understand the first point? Yes, we have to understand the whole question. Yes, actually, this is the last part, okay, and the last part usually they make it a little bit confused, okay, in the last past papers. Okay, so again, the manufacturer wavelength will be shorter, okay, since the frequency needed for the photons, it will be having least energy. Okay, so that means lower wavelength will get a higher value of 1 over L. Okay, so that means it will what? Shift the values to the right. Okay, it will be higher. So whenever the values, okay, are smaller, okay, longer of wavelength, that means the 1 over lambda will be what? Shifted with less value. Okay, that means it will decrease what? The gradient. So instead of having the gradient like this, okay, the gradient will be something like this. So this gradient. Okay, so whenever we have less gradient, okay, not like this, it will be a little bit less. Okay, that means what? Like this. Okay, it will be like this. That means what? Whenever we have less gradient, that means the Planck constant will be what? Will be smaller. Good. And that's it. We are done by this exam. Do you have any question?